In this video, we're going to begin our discussion of runtime systems. Now, at this point, we've actually covered the entire front end of the compiler, which consists of the three phases: lexical analysis, parsing, and semantic analysis. And these three passes, or these three phases together, their job is to really enforce the language semantics, or the language definition. So we know after these three phases are done that if no errors have been generated by any one of those phases, then the program is actually a valid program in the programming language that we're compiling. And at this point, the compiler is going to be able to produce code, to produce a translation of the program that you can actually execute. And I should say that, of course, enforcing the language definition is just one purpose of the front end. The front end also builds the data structures that are needed to do code generation, as we've seen. But there is a real change. Once we get through the front end, we're no longer looking for errors in the program. We're no longer trying to figure out whether it's a valid program. Now we're really down to the point where we're going to generate code. And that is the job of the back end. So code generation is certainly part of it. The other big part of the back end is program optimization, so doing transformations to improve the program. But before we can talk about either one of those things, we need to talk about runtime organization. And why is that? Well, because we need to understand what it is we're trying to generate before we can talk about how we generate it and have that make sense. So first we're going to talk about what the translated program looks like and how it's organized, and then we'll talk about algorithms, code generation algorithms for actually producing those things. And this is a well understood area, at least there are some very standard techniques that are widely used, and those are the ones we're going to cover and encourage you to use in your project. The main thing we're going to cover in this sequence of videos is the management of runtime resources. And in particular, I'm going to be stressing the correspondence and the distinction between static and dynamic structures. So static structures are things that exist at compile time, and dynamic structures are the things that exist or happen at runtime. And this is probably the most important distinction for you to try to understand if you really want to understand how a compiler works. What happens at compile time and what happens at runtime, and having a clear separation in your mind between what is done by the compiler and what is deferred to when the target program or the generated program actually runs, that is key to really understanding how compilers work. And we'll also be talking about storage organization, so how memory is used to store the data structures of the executing program. So let's begin at the beginning. So initially, there is the operating system, and the operating system is the only thing that is running on the machine. And when a program is invoked, when the user says he wants to run a program, what happens? Well, the operating system is going to allocate space for the program. The code for the program is going to be loaded into that space. And then the operating system is going to execute a jump to the entry point, or the main function of the program, and then your program will be off and running. So let's take a look at what the organization of memory looks like very roughly when the operating system begins execution of a compiled program. So we're going to draw pictures of memory like this. There'll be just a big block, and there'll be a starting address at a low address and a high address, and this is all the memory that is allocated to your program. Now, into some portion of that space goes the code for the program. So the actual compiled code for the program is loaded usually at one end of the memory space allocated to the program. And then there's a bunch of other space that's going to be used for other things, and we'll talk about that in a minute. Before going on, I want to say a few words about these pictures of runtime organization, because I'm going to be drawing a lot of them over the next few videos. So it's just traditional to have memory drawn as a rectangle with the low address at the top and the high address at the bottom. There's nothing magic about that. It's just a convention. We could just as easily have reversed the order of the addresses. It's no big deal. And then we'll be drawing lines In this video, we're going to begin our discussion of runtime structures with the notion of procedure activations. Before we begin the discussion of activations, it's worth being explicit that we have two overall goals in code generation. One is to be correct, to generate code that actually faithfully implements the programmer's program. And the second is to be efficient, that code should make good use of resources, and in particular, we often care that it run quickly. And it's very easy to solve these problems in isolation. If all we care about is correctness, it's not a hard problem to generate code that's very simple but also very slow and correctly implements the program. If all we care about is speed and we don't care about getting the right answer, the problem is even easier. I can generate extremely fast programs that generate the wrong answer for any problem that you care to name. And so really, all the complications in code generation arise from trying to solve these two problems simultaneously. And what has grown up over time is a fairly elaborate framework for how a code generator and the corresponding runtime structures should be done to achieve both of these goals. Okay? And the first step in talking about that is to talk about activations. We're going to make two assumptions about the kinds of programming languages for which we're generating code. The first assumption is that execution is sequential. Given that we execute a statement, the next statement that will be executed is easy to predict. In fact, it's just a function of the statement that we just executed. So control is going to move from one point in a program to another in some well-defined order. The second assumption is that when a procedure is called, control will always return to the point immediately after the call. That is, if I execute a procedure F, and once F is done executing, control will always return to the statement that followed the point where F was called. And there are certainly programming languages and programming language features that violate these assumptions. So the most important class of programming languages that violate assumption one are ones that have concurrency. So in a concurrent program, just because I execute one statement, there's no easy way to predict what the next statement is that will be executed because it might be in a completely different thread. And for assumption two, advanced control constructs, things like exceptions and call CC. If you happen to know what call CC is, it's not important if you don't. These kinds of constructs that affect the flow of control in fairly dramatic ways can violate assumption two. So in particular, if you're familiar with catch and throw style exceptions in Java and C++, when we throw an exception, that exception might escape from multiple procedures before it is caught. And so there's no guarantee when you call a procedure, if that procedure can throw an exception, that control will ever return to the point immediately after the procedure call. Now we're going to keep these assumptions for the rest of the class. We may later on in future videos briefly discuss how we would accommodate some of these more advanced features. The material that we're going to cover is basic to all implementations, and even languages that have concurrency and exceptions build upon the ideas that we're going to discuss here. So first, a definition. When we invoke a procedure P, we're going to say that that is an activation of the procedure P. And the lifetime of an activation of P is going to be all the steps that are involved in executing the procedure P, and including all the steps in the procedures that P calls. So it's going to be all the statements that are executed between the moment that P is called and the moment that P returns, including all the functions or procedures that P itself calls. We can define an analogous notion of the lifetime of a variable. So the lifetime of a variable x is going to be the portion of the execution in which x is defined. That means that it's all the steps of execution from the time that x is first created until the time when x is destroyed or deallocated. And just note here that lifetime is a dynamic concept. So this is something that applies to the executing program. We're talking about the time when the variable first comes into existence until the moment in time when it goes out of existence. And scope, on the other hand, In the previous video, we talked about activations, but we never said what information we actually need to keep for an activation. That's the topic of this video. An activation record is all the information that's needed to manage the execution of one procedure activation. And often this is also called a frame. That means exactly the same thing as activation record. These are just two names for the same thing. Now, one interesting fact about procedure activations is that they have more information in them than you might expect. So in particular, when a procedure F calls a procedure G, the activation record for G will actually have information not only about G, but very frequently also about the calling function F. So typically the activation record for a procedure will contain a mixture of information both about that procedure and about the procedure that called it. Now, up to this point, we haven't said why we need to keep information about activations at all. And the reason is that there is some state associated with each procedure activation that is needed in order to properly execute the procedure, and we have to track that somewhere. And that's what the activation record is going to be for. It's going to be to hold the information needed to properly execute the procedure. So let's look at that in a little bit more detail. Let's consider the situation where procedure F calls procedure G, and what is going to happen. So conceptually, what happens when F calls G is that F is suspended. F is going to stop executing while G is running. So G is going to be using the processor and all the resources of the machine. But when G completes, we want to start executing F again. F is going to resume. And so in between, while G is running, we have to save the state of the procedure activation of F somewhere so that we can resume it properly. And that's, again, what the activation record is for. And so G's activation record is going to have information in it that will help us to complete the execution of G. So there'll be some information about G that we just need in order to run G, but also G's activation record is going to have to store whatever we need to be able to resume the execution of procedure F. So let's work through an example. Here's one of the programs that we looked at in the last video, and here is a design for a concrete activation record for the procedure F. So we'll have one position for the result of F that will hold the return value after we've finished execution of F. There'll be a position here for the argument to F. So F only takes one parameter, so only need one word here to hold the argument to the function. There'll be a control link, so a pointer to the previous or the caller's activation. And we'll also have a slot for the return address. So the address in memory, or the address of the instruction that we are supposed to jump to after the execution of F completes. So now let's just execute this program by hand and work out what the activation records will look like on the stack. So when the program is first invoked, it will call main. There will be an activation record for main. Okay, but we're not going to worry about that. We're just going to focus on F. So there's some stuff for main, but we're not going to talk about that. And then main is going to call F. All right, and so when main calls F, an activation record will be pushed onto the stack. We'll have four slots in it, or four fields for values. And what will go in those? Well, the first slot is for the result. Well, it's just starting to run. F is just beginning execution, so there's nothing to put there at the moment. That gets filled in when F returns. The second position will hold the argument to F, so that'll be the number 3. The third slot will hold the control link, so that's going to point back to the activation for main. And the fourth position will hold the return address. And this is actually not completely trivial because F is called in multiple places. So if you look at the program, there's a call to F in main, and there's a call to F inside of F itself. And so depending on where the function is called from, after that function completes, we want to return to a different address. In the case of main, when this call to F completes, we want to return to the whatever instruction comes after the call to F, which is just going to be something that wraps. In this video, we're going to continue our discussion of runtime organization by talking about how compilers handle global variables and heap data structures. Let's start by talking about global variables. The basic property of a global variable is that all the references point to the same object. That's what it means to be global. And for this reason, we can't store a global variable in an activation record, because the activation record, of course, is deallocated when the activation completes, and that would deallocate our global variable. So the way global variables are implemented is that all globals are assigned a fixed address once, and these variables with fixed addresses are said to be statically allocated because they're allocated essentially at compile time. So the compiler decides where they're going to live, and then they will live there in all executions of the program. And depending on the language, there may be other statically allocated values, and we'll actually see some later on, but they behave just the same as global variables. So adding global variables changes our runtime organization picture a little bit. First, we have the code as before, and then immediately after the code is typically all of the static data. So these are the global variables and other static objects, things that have fixed addresses for the duration of the execution of the program. And then the stack comes after that. So the stack will start at the end of the static data area and grow towards the end of the program's allocated memory. Turning now to the heap, any value that outlives the procedure that creates it also cannot be stored in the activation record. Let's take a look at this example. So here we have a procedure foo, and let's take a look at the activation record or frame for foo. And let's say that the foo allocates a bar object, and that we're going to store that object in foo's activation. And now when this method returns, of course, the activation record will be deallocated, and so the bar object will also go away. But that won't work here because notice that the dynamically allocated object, the object we allocated during the execution of foo, is also the result of foo. And so this has to be accessible to foo's caller after foo exits. And so what that means is that this bar object and all dynamically allocated data have to be stored someplace other than the activation record. And languages with dynamically allocated data generally use a heap for that purpose. At this point, we can summarize the different kinds of data that a language implementation has to deal with. First, there is the code. And in many languages, I shouldn't say most, in many languages, the code is a fixed size and read-only. That means that the compiler creates all the code that will be used in the execution of the program, and that can be allocated once. I should say that there are many languages also where this is not true, and code can be dynamically created at runtime. The static area would contain data with fixed addresses, and this would be things like global variables. And this is also typically fixed size, but it may be readable and writable, as opposed to the code, which you generally don't want to be able to write. And then a stack is used to contain an activation record for each currently active procedure, and the activation record is generally fixed size, so each activation record for each particular kind of procedure has a fixed size, and this will contain all the local information, the local variables and temporaries needed to execute a particular activation. And finally, the heap is for everything else. So the heap is just for all the data that doesn't fit into one of these other categories. This includes all the dynamically allocated data. And if you are familiar with C, the heap in C is managed by the programmer using malloc and free. In Java, you have new for dynamically allocating data, and then garbage collection actually takes care of reclaiming data from the heap that's no longer used. Now, many language implementations use both a heap and a stack, and there's a little bit of an issue here because both the heap and the stack grow. And so we have to take care that they don't grow into each other and step on each other's data. And there's a very nice and simple solution to this, and that is to start the heap and the stack at opposite ends of memory and let them grow towards each other. So let's take another look at our runtime organization picture. And just to review, first we have the In this brief video, we're going to talk about alignment, a very low-level but very important detail of machine architecture that every compiler writer needs to be aware of. First, let's review a few properties of contemporary machines. Currently, most modern machines are either 32 or 64-bit, meaning they're either 32 or 64 bits in a word. And the word is actually subdivided into smaller units. We will say that there are 8 bits in a byte, and then 4 or 8 bytes in a word, depending on whether it's a 32 or 64-bit machine. And another important property is that machines can be either byte or word addressable, meaning that in the native language of the machine, in machine code, it may be possible to either name only entire words, or it may be possible to reference memory at the granularity of individual bytes. We say that data is word aligned if it begins at a word boundary. So if we think about the data in memory or the organization of the memory and it's laid out into bytes, and let's say that this is a 32-bit machine, so that 4 bytes make a word, and one word begins here, and the next word begins here. Then if data is allocated on a word boundary, say in these 4 bytes, then that would be a word-aligned piece of data. If a piece of data begins in the middle of the word, so let's say, for example, that it begins here, we have some data that's allocated here, this data is not word-aligned because it doesn't begin on a word boundary. And the important property, or the important issue, is that most machines have some alignment restrictions. And these restrictions come in one of two forms. So on some machines, if the data is not properly aligned, meaning that you try to reference data that isn't aligned the way the machine requires, then the machine may just fail to execute that instruction. Your program may hang, or even the machine may hang, but the important thing is that the program will not execute correctly. So it's incorrect to not have the data aligned properly. Now there are other machines that will actually allow you to put the data anywhere you like, but at a significant cost. So it may be that accessing data that is aligned on word boundaries is cheaper than accessing data that's on non-word boundaries. And these performance penalties are often dramatic. So it can easily be 10 times slower to access misaligned data than to access data that has the alignment favored by that particular machine. So let's take a look at an example where data alignment issues tend to come up. One of the most common situations where we have to worry about alignment is in the allocation of strings. So let's say we have this string, the string hello, and that we want to put it in memory. So let me draw our memory as a linear sequence of bytes. Okay, so I'm going to mark out some bytes here. And let's assume this is a 32-bit machine, so let me make the word boundaries a little bit heavier boundaries. So 1, 2, 3, 4. 2, 3, 4. Okay, so there are the word boundaries. And now let's say that we're trying to have aligned data, a word-aligned data, and so we'll allocate the string beginning on a word boundary. So the H character will go in the first byte, then E, then L, then L, then O. And now we may have a terminating null, depending on how strings are implemented, but let's assume that we do. And this is a fine placement of a string. The string begins on a word boundary, and that will satisfy, presumably, any alignment restrictions of the machine. And now the question is, where does the next data item go? So we could begin the next data item right in the next available byte, and that would be good if we were very concerned about not wasting memory. But notice that that data item will then not be word aligned, and we may either run into correctness or performance problems if the machine has restrictions on alignment. So the simple solution here is to simply skip to the next word boundary and allocate the next data item, whatever it is, on the In this video, we're going to move beyond our discussion of runtime organization and begin talking about code generation. And in this first, this will be quite a long series of videos on code generation. We're going to talk about the simplest model for code generation, which is called a stack machine. So in a stack machine, you might guess that the primary storage is some kind of a stack, and you would be right. In fact, the only storage that a stack machine has is a stack. And the way a stack machine works is that it executes an instruction. All instructions have the form. There's some function of some arguments, and they produce one result. And what that does is it'll pop n operands from the stack. So the arguments a1 through an are stored at the top of the stack. It will then compute the function f using those operands, and it will push the result r back on top of the stack. Okay, so let's take a look at a simple example. Let's see how we would compute 7 plus 5 using a stack machine. So we would have our stack, and initially the stack might already have some stuff on it, but we don't care what that stuff is. And so to execute 7 plus 5, what we would do, well, first we will have to get the 7 and the 5 onto the stack. So as we get pushed onto the stack, and we'll say more about how that happens in a minute. But let's say that 7 and 5 are both on the stack. And so now we want to compute the addition of 7 and 5. So addition takes 2 arguments. So we would pop the 2 arguments off the stack. Okay, we would wind up with the 5 and the 7 popped off the stack. We would perform the operation plus, and then the result would get pushed back onto the stack. So this would be equal to 12, and then 12 would get pushed back onto our stack. Okay, and now notice that I did indicate that there might be some other stuff on the stack already. Let me just give that stuff a name. And let me talk about one very important property of the stack machine. So notice that when we evaluated 7 plus 5, we wound up in a situation where the result of that operation was on top of the stack, okay, and the initial stack contents was unchanged. This stack, the stuff that was below the arguments that we were interested in, didn't get modified. Okay, so it survived through all the operations unchanged. And this is an important property of a stack machine that we will exploit. And the general, and just to say what the general property is, when you evaluate an expression, the result of the expression will be on top of the stack, and the contents of the stack prior to beginning evaluation of the expression will be preserved. So now let's think about how we could program a stack machine. So let's have a language with just 2 instructions in it. We can push an integer onto the stack, and then we have the operation add, which will add the 2 integers at the top of the stack. And now let's take a look at this program, which pushes 7 and then pushes 5 and then does an add. And so let's think about how this program would work. Okay, so we have our stack contents, and now the first instruction is to push 7. So we wind up with a 7 on the stack, added to the stack, and now we push 5. Okay, so in the next step, we'll have 5 and 7 on top of the stack. Then we'll perform the add, and that will pop these 2 elements off the stack and add them and push the result back on. And we'll wind up with 12 on the stack. And again, the original stack contents are preserved. Now, one interesting property of stack machine code is that the location of the operands and result is not explicitly stated in the instruction. And that's because these instructions always refer to the top of the stack. And this is in contrast to a register machine or register instructions that explicitly name where they take their operands from and where they put their results. So for example, you might be familiar from seeing some machine code or assembly code in the past that an add instruction might typically take 3 registers, 2 for the arguments that are 2 for the register arguments that are going to be added together, and 1 for the destination for the result. Whereas in the stack machine, we just have a single word add and no explicit naming of the arguments, because it's fixed where the arguments will come from. The arguments will always be popped from the stack,